All right, then. Okay. So just a quick review on the valves. We have lift check valves and swing check valves. All right. This right here is a lift check. All right. And then what we have here is a swing check. Big difference between the two, as we saw with our valves, is a lift check, one, can't be mounted vertically. They can only be mounted horizontally. All right. Swing checks can be mounted vertically and or horizontally. Okay. So a lift check valve is a check valve in which the disc, sometimes called lift, can be lifted up off its seat by higher pressure of an inlet or an upstream fluid to allow flow to the outlet or downstream side. All right. So again, you're going to have flow that's going to be going in this tube, and that's going to be pushing up against this disc right here. And it's going to be counteracting the spring force. And that's what's going to allow flow. And as soon as this pressure is lost, you are not going to be overcoming that spring force, and it's going to lock close. All right. A check valve operates in a similar sense, but there is no spring. All right. What it's utilizing is the weight of the disc. All right. To check valve in which the disc is a movable part of a block that flows, swings on a hinge either into the seat or the block, and reverse flow or off the seat to allow forward flow. All right. So same principle. You have flow going in this direction. It's going to be pushing against this disc, and you're going to have flow that's going around it and keep going. And as soon as this is lost, any flow that's going to go in reverse, this swing check is going to come backwards with the weight, and it's going to close off and not allow any backflow. All right. So let's talk about heat exchangers and coolers. Heat exchangers transfers heat from one substance to another. All right. One substance needs to be hotter than the other. Heat flows from hot to cold, and the greater the temperature difference, the faster the heat transfer. All right. What is it called, a heater or a cooler? And it depends on what heat transfer you want. Classification is by the path of the heat flow. Indirect or surface, through the plate tube or other. And direct contact is fluid to fluid. And then relative direction of fluid flow. So you have parallel, you have counter, and you have right angles as a cross flow. All right, and then contact, again, direct or indirect. And what do we mean by parallel or counter or right angles? So starting with right angles, what you'll have is that two pieces of your flow will look like this. You have your hot fluid, and then you have your cold fluid. And they're flowing at a right angle to each other. All right. Parallel is like this. Now remember, these are still all in non-contact with each other. There's going to be plates separating or tubes separating them. All right. So parallel is like this right up here. And then what would be counterflow?
The opposite direction.
Say again?
The opposite direction.
Well, they're
Instead of
flowing.
running.
Exactly. Opposite directions of each other. Now, let's take a quick look. What does the right angles flow look like? What type of heat exchanger does that look like to us?
Direct contact.
It's not going to be direct contact.
The one with the tubes, and you have the seawater touching the tubes.
Yes. So that's a shell and tube type heat exchanger. All right. Normally what we would see is it's like this, right? We have our shell, and our shell is where all the cold or the hot, depending on what we're trying to do. So we'll say the shell is with the hot fluid. We're going to say it's the main condenser. All right. And then we have the cold fluid going against it. So all of the hot steam is coming through. Going like that over the cold seawater. And that's a shell and tube type heat exchanger. That's a right angle type heat exchanger. So out of all of these, one of the best ones that you can have are these counter and these right angle ones. All right. The counter ones are spectacular in the fact that if you have a really, really hot fluid over here, where it's like 90 degrees, by the time it gets all the way onto the other side, let's say it drops 10 degrees. All right, that heat has to go somewhere. The good thing about these counterflows is that if you have, like, let's say a 50 degree seawater on the start and it goes up 10 degrees, what's the nice thing about those numbers? What is the biggest thing that we see there? Remember, we talk about with any type of heat exchanger, the greater the temperature difference, the better the heat exchange, the faster it will happen. So what can we deter? What do we think about this example over here, the 80 degrees to 90 degrees and the 60 to 50? So it did all transfer from the hot to the cold one. But what else is happening? Remember, they're in contact with each other at their points. This point right here is in contact with that point. All right. Same with point 3 and point 4. Point 1 and 4 are not in contact with each other. Same thing with 3 and 2. 1 and 2 are in contact with each other. 3 and 4 are contact. And we can go down that whole line. But the biggest thing about these counter flows is that you keep your high temperature difference. All right. You have that large delta T. From 60 to 90 is a larger delta T than where if you would have it the opposite way. Same with 50 to 80. All right, so if we look up on the parallel flow, and let's say we have almost the same thing. We have 60 coming out. We have 50 going in. And what did I say? 90 coming in, 80 going out.
Yeah.
All right. So if we look at it that way, point one and point two are in contact with each other. Yes, they have a greater differential right there than what we had over here of 90 to 60. But look on the outlet now. 60 to 80 is a much smaller differential. And that's going to be true along the entire line of your entire heat exchanger. All right. And you may not even get these nice even numbers with a parallel flow. It will probably be less. All right. Because you don't have that great of a heat transfer, because you don't have a large delta T throughout the entire flow. All right. Remember, with heat transfer, it's time in contact with each other, and your delta T. Those are the two biggest pieces. All right. Can I go on to the next slide, or are you guys still copying some stuff down? You guys good?
You're good.
Okay. So classification continued by the number of passes. So you have single pass. That's fluid in one direction only. All right, so they just pass each other once. Two passes is the fluid changes direction in the second pass. Four passes, multiple times, and additional passes. All right. All right. Let's go on to parallel flow. Here we go. Everything that I just went over. All right, so basically we have the hotter fluid, the colder fluid, slower rates to the transfer outlet, less effective. Counterflow, less area required to remove heat. Heat transfer equal at all points. It's the most common. All right, like I said, it's the best version. You're literally not changing anything inside of the mechanism. The only thing that you're changing is the direction of one of your fluids, and you gain so much. So there's not even any more of an expense for companies to put these in. All right, and then cross flow, as we talked about, at a 90-degree angle. All right, so shell and tube type heat exchangers, they look like this. All right, lots of tubes. There's your shell. All right, and inside of your shell, you have all of these tubes, as you can see, and they're massive tube bundles. All right. Then you have a plate type heat exchanger. Those are those big plates that I brought into class. One side of the plate will be hot, one side of the plate will be cold, and it's going to be alternating all the way down. All right, and you can see what you have is you have the fluid flow on one side and no fluid on the other. So this could be your cold over here. And over here will be your hot fluid that's going through these little pipes. All right. And then your next plate will be your hot here and your cold over here. All right. So whilst this whole plate is hot, this whole plate over here is cold. And that's what's allowing your flow is these gaskets here. The makeup of a plate type heat exchanger. Someone say something? Okay.
No, it was just you. It like kind of glitched out.
Ah, okay. Sounds good. All right. So plate type heat exchanger components. So you have a couple pieces here. You have your hanger. You have your gasket. That's a very important part there. All right. That's going to be controlling all of your flow. And it's also going to be sealing it. All right. You have your bridge zone. You have your leakage chamber. That's going to see if there's any leakage that's coming in. See how there's another gasket right here? It's going to stop any of that fluid from mixing. All right, so it's a backup. All right, you have the diagonal grooves. That's going to allow the flow to go in one direction and come out. So it's not all just going to dribble out over here. All right, fluid's going to flow all out. You have your distribution center. That's going to channel it again. So that way you have optimal flow going through the entire plate. And then this whole red zone here is your main heat transfer zone. All right.
Could you go back to the slide that had like the side view?
Yes.
Thanks.
There's a question in the chat that says, can we change the gasket if it fails, or should we just change the whole plate? Pretty much those things are glued on. So you're going to have backup plates, and you can remove one of the plates. You just basically, you would order a new plate.
Alrighty, thank you.
Yep. Chat. All right. So you have these high performance seals. You have your gaskets along the side, and you can see basically here where it's making that seal. Right? Not only is it sealing the fluid from coming out, it's sealing the fluid from each other as well. All right. So let's get into distilling plants. So a basic distilling plant. All right, you have your heat source. You have your salt water. Remember, we're going to be utilizing salt water. All right. We turn it into a vapor. That vapor is going to be just water at that point. All right. And this is called our evaporator. It's evaporating. Okay. So that vapor goes through a pipe. It's removed from the evaporator. And as it goes through a pipe, it goes into a condenser. It's condensing back into a liquid. All right. And we're removing our heat that was given to it in its heat source. Okay. We have now turned it into a different type of liquid. It's called a distillate. All right. So it's distilled water. Now, as we remove more and more salt water, we need to add it back in. So we have something called a feed pump. So we have our salt water supply. All right. It's entered in. And now we have something called a distillate pump. And we are removing all of our distillate that's been created. And that's going to our distillate tanks or our potable water tanks. All right. Now, the big byproduct that comes from this process is brine. All right. When you boil salt water, Part of the process is yes, you're getting clean vapor, clean H2O coming from it. But what you're leaving behind is all of the minerals, all of the salts, everything anything that's not hydrogen and oxygen. All right. And that's it's called brine. And we have to get rid of it somehow. All right. We have a brine pump, and basically all it's doing is taking the brine and ejecting it overboard. Now, right there, as you saw, we changed something. Right where we're at right now is the basic starting point. We have a heat source. We have a heat sink. We have a feed pump. Everything's all great. All right. And the next thing that happens here is we're going to be adding efficiency to it. All right. Because at this point in and of itself, this is fine. All right. But to gain efficiency, and that's the biggest thing we're always after, is where we can squeeze more energy out. And that's done right here. All right. Instead of using just regular old salt water that you're not going to use again, you might as well use the heat that you're going to not use after it goes into the condenser to preheat your feed water. All right. So you're banging out two things with one stone. You're cooling your distillate into a liquid that's pumpable. All right. And you're heating up your feed water. And the last thing we also have here, if you look, what's going on at that point? What type of heat exchanger are we doing here? We have a cross flow right there, but we're also doing something else. Our big heat exchanger, if you were to put a circle around this whole piece, what also is happening? It's another type of heat exchanger that we have.
Is it parallel?
Nope. Parallel would be as if they were flowing in the same direction. This is going to be counter. Okay? But that's the giveaway right here in this little spot. All right? We have our coldest point is going to be going against the spot that's not at the hottest. All right? So it's going against, and it's just getting a little bit more heat out of that distillate. All right, the distillate's coming out of a pump. It's cooled off to the point that we can pump it. But that's, 211 degrees Fahrenheit. We can get more out of it. And so we still have a great heat transfer ability, and that's what we're doing, is we're gaining a little bit of more efficiency right there before we send it in and cool off our distillate. All right. Any questions on this before we go on? Do you guys want to take a quick break, or do you guys want to continue on?
Quick break.
Okay. So let's go at 10:35. Give you 15 minutes or so. 10:35, 10:40. All right, let's get going. First things first, I'm trying to figure out, Brian, are you on a loop or are you actually just drawing something?
Oh, I'm just drawing something right now.
Okay.
Like I can write like all the notes and everything.
All right. So let's go on about distilling plants. So as we go through, we're going to talk about high pressure and low pressure systems. All right. And high pressure is anything that's above atmospheric. All right. So atmospheric, as we've talked about before, is what we're standing in right now. It's at sea level. All right. And thank God this is a shipping class because everything will be at sea level. All right. So we have to only worry about our absolute pressure is at 14.7 psia. All right. Now, if that was PSIG of gauge, that would be at 0. Okay. Now, PSIG, as we talked about, is pressure gauge. All right. It's different types of readings that you can get, different types of gauges that are out there. All right. Where it takes it 0 point being 1 atmosphere. All right. Now, we also have inches, how it can be measured. All right. And that's when you go into vacuum. And then where we have here is our boiling point of water in Fahrenheit and in Celsius. So as you see, as we go up in pressure, we are going to be increasing our boiling point. All right. And as we decrease in pressure, we are decreasing our boiling point. So they're directly related to each other. All right. So most people is what they talk about is when they talk about lack of pressure or anything else like that. The biggest thing is that you have to always kind of think to yourself, um, is what chart or what frame of mind you're in. All right. Now, most of the time is if someone's going to be talking about PSIA, they're going to stick to it. All right. But a lot of the times of what you're going to be in is you're going to be in this pressure relative or PSIG. Okay. And this really should say PSIG right there. Now, what we're going to have is that's where you have to keep your mind at. As soon as you enter inches, you know you're in a vacuum. All right. Even though this is 10 PSIA over here, that's still under a vacuum. Okay. And that's the biggest thing we have to keep in our mind is where we're at and where we are in the chart. All right. And low pressure is anything under a vacuum. So a high pressure example is the contaminated evaporator. All right. And we have our heat source right here is 150 PSI auxiliary steam. All right. It's returning to the DC heater. So that goes in, goes out, it's done. It did its job. It's given off its heat. So we have 40 PSI vapor at 285 degrees Fahrenheit. That is at its boiling point. All right, so we're using a lot of energy here to boil water. You know, we almost doubled. We're above double of our, not double, I'm sorry. We're almost at another 100 Fahrenheit needed. And we're at 40 PSI. Why are we wasting so much of our auxiliary steam to do that? And it's all going to where it's going. Your fuel oil heating, your gallery steam, and your lube oil heating. All right. The one thing that we have to know about the fuel oil on the TSES is that if you take one, let me start over. The fuel oil on the TSES, what the boilers were designed for, one more step in quality down is what? What do you think how nasty of fuel do you think we use on the TSES?
Is it two oil?
No, we actually use letters.
What do you mean by nasty of fuel?
So like when you let say like when you take like a cup of water and you dip it into like a pond and you let it sit and all the densities filter out of it, you have like the really nice clean stuff on top and then it just kind of goes through. The same thing kind of happens with fuel oil. Right? When you pull out oil from the earth, it has every single level of fuel in it, and diesel being the nicest, and it usually sits up on the top. All right, and then it goes down from there. You have gasoline, then you have home heating oil, and then you have pulling on my own brain of how long ago I learned this, but there's certain layers. All right, and we basically we have to use this fuel oil on this level. The next level is what our boilers were designed for. And the next level below that is asphalt. So the stuff we use on the ship is bunker B. All right. And we were designed to use bunker C. And the stuff below bunker C is asphalt. That's what they make roads out of. So our boiler, and again, we don't use bunker C because we can't get it anymore. They use the cheapest stuff they could possibly do. So think about asphalt. Has anybody seen asphalt being poured? And how slowly it moves, even though it's like wicked hot. It would burn you as all hell if you were to touch it. And it's super hot of what's going on. We have to heat our fuel oil, because it's not that much better than asphalt, in order to move it. All right. It's almost like a solid gelatin when it sits in our tanks. So when it goes to these heaters, the biggest thing we want to do is that we don't want any of our heating. We don't want our steam to go anywhere near that. All right. Again, think about last semester when we were talking about the steam cycle. We want to use as much energy as we possibly can. And part of that is returning stuff to the DC heater. So what we do is we try to avoid any direct contact with this crazy heavy fuel or our lube oil, which isn't anything bad. It's not like it's this heavy, crappy stuff, but it's still something you don't want to get contaminated into your steam. We don't even want salt in our steam. Can you imagine what lube oil would do to it? So what we do is we avoid all of that by using a high pressure system. It's at 40 PSI. So that way, when it goes into these tanks, and these tanks are sitting at almost atmosphere, they will be underneath the high pressure. So if there is any leakage, the steam that's here, this contaminated vapor, will be the one that's in contact with it. And that will leak into our fuel oil and into our lube oil, into our gallery steam. And it'll leak into that, and our fuel oil will just sputter a little bit. It won't be a problem. Our lube oil will take care of in the purifiers, and it'll clean it out. Not a problem. Gallery steam, doesn't matter. So when we turn these systems off and they're no longer under this 40 PSI pressure, that fuel oil, that lube oil can leak into it and go back into it. And again, that is where a contaminated drain tank comes in. Okay? And why this is all in its own self-contained loop. We can see into this contaminated drain tank because it's that atmosphere. And we can see if any of these systems are leaking, if we have any problems. And again, it's high pressure to protect this system. But when it's not in use, we have our ADT, our contaminated drain tank, to inspect for it. All right. Now, this is utilized on a float switch. So when the level gets low, turns on the feed pump, it pumps stuff out of the contaminated drain tank, it goes back up, fills it back up. All right. And it basically just stays on that cycle. Any questions on what is going on with our high pressure evap system? Or why we use a high pressure system or anything like that? Okay.
We use the lower grade oil just because it's cheaper.
Yeah, and also when you guys go on a cruise, you actually see it. It's not only is it old, the ship, but it's it really shows how much it really is designed for that lower end fuel. And you'll see it when we go into port, and that's the biggest example. See, you don't have a frame of reference for bunker C. No one does. I don't either. We couldn't even get it when I went to school. But it was designed for this lower end fuel, not because of our school wanted it, but because the company that built the ship wanted the cheapest way to steam across the ocean. Where can you lower your cut your cost? And fuel is one of the biggest costs. So when we go into port, certain ports will have restrictions on how far out you have to be, like Denmark. When we go into you guys are probably going to go to Copenhagen one of these years. When you go into Copenhagen, when you're a certain distance from them, you got to switch over to diesel fuel, because it's the cleanest burning. They don't want any sort of smog coming anywhere near their country, so they'll have you switch over to diesel fuel, miles out when you're out at the sea buoy. All right. And when we come into port, you'll see the burners. They are sputtering. They're not happy. The engine is not running happy. And it's only really a problem for like us steamships. Diesel ships are fine. They're either running on full diesel or they got their heavy fuel that they run on. And when they come into port, it's a diesel engine. It runs fine on diesel. But you'll really, really see it when we come into port or when you're standing your port watch, especially when you're watching those fires. And as a mug, that's one of the big things that you do on your watch is doing fire watching. You'll really start to understand those fires that are being used and how important fuel is and the right fuel and what engines are being designed for. So, all right. And now this is our contaminated drain tank. All right. And she looks exactly as I picture her. So when you look inside of it, you basically pull up one of these two rocks right here or right here. And you can look in and you can see basically if you have any layer of fuel or any of the lube oil or anything that's leaked into it. And it's basically just an inspection. All right. It allows you to look into those tanks and see what's going on without actually having to physically go into them. All right. So, any other questions before I go jump into low pressure? Okay. So, low pressure evap. All right. So, we're going to go into the first one. This is submerged tube type evaporator. Okay. This is the big thing about these things I want to bring up. When you look at these submerged tube type, yes, the big thing is that it's using submerged tube in order to heat the seawater and turn it into a vapor and go from there. Yes, that's the big identifier, and that's why we call it a submerged tube type. But the other thing that you have to recognize is that, where the heating is taking place. And the heating is taking place in the evaporator. All right. The feed water is entering at 130 degrees Fahrenheit. It is, even though we're at 3 PSIA, which is about 24 inches of vacuum. Remember, 30 inches is a perfect vacuum. All right. So we're damn near close vacuum. Okay. So even though at 130 degrees is being entered, it only has to go up like 10 or 15 degrees in order to boil. And that's all this 5 PSI auxiliary steam is doing. All right. But we have to always think about our heat source and where it is in the system. Okay. So as we go through, we boil our water. All right. We still have our brine ejector. It's still going overboard. That's still our excess salt water. It's heavily dense salt water that's not going to be able to boil. It goes through and our steam travels up this line. And we go to our 150 PSI auxiliary steam. That's our first thing that we're going to be hitting after. We go through our condenser and we become distillate. All right. And we're giving off our heat to the feed water. All right. And that feed water is going off, and that's going to hit our 150 PSI auxiliary steam. So there is a lot going on here, but let's just go and start at our feed pump. Our feed pump comes up, and again, we go to a distillate cooler. All right, so we're cooling down our distillate, and we're gaining a little bit more heat. All right. Then from our distillate cooler, we go into our condenser. we touch this really hot vapor comparatively. It's 142 degrees. All right. And we go into our air ejector. And our air ejector is a mix. We got an air drag line, and we have 150 psi auxiliary steam. So our air drag line is removing any of the non-condensables from the system, and it's basically creating a vacuum, and it's constantly keeping that vacuum. Okay. And as we go through, we now have a mixture of contaminated steam now. Our 150 psi auxiliary steam is now contaminated. All right. And since it's contaminated, it has to go to our basically our contaminated drain tank, our and it goes elsewhere into the system. We're done with it, and we're grabbing as much heat as we can. And that's how we're getting to this 130 Fahrenheit feed water before it enters into the system. It comes from our distillate cooler, it comes from our condenser, and a lot of it comes from our air ejector. All right. So when we talk about air ejectors, we talk about the Venturi effect. All right. And the Venturi effect is basically you have an inlet and it's a high pressure. All right, so this would be our 150. Auxiliary steam. All right. And now your suction, that's going to be coming from, that's your air drag line. All right, that's this. That's from your evaporator. All right. And the Venturi effect is the phenomenon that occurs when a fluid, seawater or steam, that is flowing through a pipe is forced through a narrow or constricted section, resulting in a pressure decrease and a velocity increase. The Venturi effect allows air to be pulled in, thus creating a vacuum within the evaporator. All right. So you can use basically, you have your ejector pump and it's utilizing salt water to do this. All right. And this is how they eject brine. So this is how it's sucking out brine from our evaporator. All right. Now, let's talk about a flash type evap. Here's the big thing is that this number changes. And that number changes due to your feed water heater. Instead of having a tube's nest in here, you now have basically a tube's nest right there. Okay. And we went from, look, 130 to 172. All right. And now as it enters, that is at its boiling point. It's above its boiling point. It's going to flash into vapor as soon as it enters. Because you remember, we're at a feed pump. We're under pressure here. We're under pressure here. We're under pressure here, here, and here. As soon as it enters into this tank, this vessel, it is at 24 inches vacuum. All right. It is no longer under pressure. And at 172 degrees Fahrenheit, it is going to flash into a vapor. All right. And this all happens due to this. All right. Under evap feed pump pressure, 15 to 20 psig, water boils at 225 degrees Fahrenheit. All right. So on this side of it, 225 is boiling point. So 172 is way under. We're good. We're not going to have any water that's going to be boiling inside of our pipes. But as soon as it goes into our vessel, as soon as that goes into the evaporator, water boils at 142. So, but each pound requires 1,000 BTU of latent heat to change phase. All right. And we talk about that whole fact of this is our latent heat. This is our sensible. All right. Remember, we're going from pure liquid to pure steam just on one side to the other of this device. We're going from here of 172, and this is 225, and we're jumping all the way over here. But not on this chart. We're jumping down here. So we're basically going from here to there because we're lowering pressure. But we still have to give up that latent heat because we're traveling this way on the chart, even though we're going down on our pressure. All right. And that's what's happening inside of this whole entire device. So in cooling of 142, each pound can donate 30 BTUs of sensible heat in the process. Therefore, it takes 33 pounds of feed cooling of 33 pounds of feed cooling to 142 in order to create 1 pound of vapor. So for every 33 pounds of feed that we put in, we get 1 pound of vapor coming out. Or the big difference between the two. Submerged tube type, the heating source is in the evaporator. All right. A flash type, the heating source is outside of the evaporator. But as soon as it enters the evaporator, it's at a lower vacuum. And it flashes instantly to steam because liquid cannot exist at that temperature at that pressure. Okay? Before we go into multi-stage, is everybody good on those two concepts?
What was the flash is outside? What was inside again? Real quick.
Submerged tube is going to be inside.
Okay. Thank you.
All right. So the submerged tube type operates inside of the evaporator as its heating source, whereas the flash type, the heating source is outside of the evaporator.
All right. Thank you.
Yep. Any other questions for? All right. So multi-stage. So this is a multi-stage submerged tube type evaporator. All right. So again, feed pump, salt water. Man. Let me follow this line. All right. Let's get this all up. All right. So as our salt water goes through, we're under our feed pump. This is a distillate cooler, so our distillate's going to go through that, and we're already going to preheat our feed water already. Now we're going to go through our distillate condenser. So we're going to be condensing any of the vapor and turning it into a liquid. So we're going to be doing a heat transfer. All right. We get to preheat our feed water again. As it comes through, we go into our air ejector. All right. So our air ejector again, it's going to be a mixture of not only the steam that it's going to be utilizing, but also any of the non-condensable gases that are in this chamber, in this vessel. And that's going to be hot. So it's going to be going through and it's going to be giving up heat again. So our feed water is getting heated again. So right now we're at what? 1, 2, that's our third time that we're heating up, and we're not even trying to heat it as its main. That's not even like a heater. We're not putting a flame to it. Our main goal here isn't to heat up our feed water. It's to cool down our distillate. It's to cool down our vapor and turn it into a distillate again. All right. And the other one is just it's garbage steam at that point. So we might as well take the heat. All right. And again, here's number 4. We are going to heat up our feed water while cooling down our vapor. And finally, it's going to be entering in. So we've had 4 times it's been heat exchanged before it even enters our multi-stage evaporator. So our first effect and second effect. First effect is at a higher vacuum. It's at a higher pressure. We are in a lower vacuum over here in the second effect. All right. So as our feed water enters, it's going to enter, it's going to get heated up. It's a submerged tube right here. So our heat source is happening inside. 5 psi auxiliary steam heats it up, turns it into a vapor. The vapor travels up. It condenses on this tube nest. All right. And now, as it goes through, it lands on this tray. It goes down. And now that's going to be a lot hotter than the feed water on this side. So as it goes through, it's going to be giving off heat, and it's going to boil off any of the liquid that's on that side, because this vapor is at 174 degrees Fahrenheit. This vapor over here is at 128. It doesn't have to give off that much heat in order for it to boil the water on this side of the multi-stage evaporator. All right. So again, it condenses on our feed water condenser. They go into a flash chamber. The flash chamber is ensuring that anything that is not a liquid will flash into either, basically if it's not at the proper state, it's going to get dragged back in, and it's going to be basically, it's a vapor, comes back in, it cools down on these coils, and then they re-enter into the flash chamber. They get sucked out by the distillate pump. They get cooled off by the distillate cooler, and then they go to our potable water tanks. Now we have a 3-way solenoid dump valve. All right, and a salinity cell. We'll talk about a salinity cell at the end, but what it's testing for is a certain level of salinity. We want to be under a certain level. And if we are above, this will dump to the bilge. If it's below the certain levels of salinity that we want, it goes to the potable water tank. So that's our automation to keep ourselves healthy, because this is going to be our drinking water. So that's all our temperatures. As you can see, we're going in. Everything here, like I said, is giving heat. We're exiting our flash chamber and going into our distillate pump at 126 degrees Fahrenheit. You know, that temperature does not need to be going to our potable tanks that are up against the hull of the ship, and seawater's at 58, 60 degrees. It does not need to be cooled off and giving off its heat to the sea. We can use that. And that's why we have these distillate coolers. All right. Same thing again, all the way through this. We don't have to just be letting the heat go to atmosphere. So, multi-stage submerged tube type evaporator. The only heat source that is externally added is in its first effect. All right. Once you get past that first effect, the vapor that comes from the first effect is now being used to heat up the second source, and so on and so forth. And the way this is possible is because each effect, as we go down, is at a lower and lower pressure. And as we go lower and lower, our temperature to boil becomes lower and lower. So this isn't, some sort of plugging an outlet, plugging in a surge protector into a surge protector situation. We are actually able to do this because of the fact that each one of these is lowering its boiling point. And we're using the energy that came from the other effect. All right. And finally, as they all come together, they go into a flash chamber. And any of this liquid that comes in, anything that doesn't condense all the way, gets sucked back up and then cooled off and then re-entered into our distillate pump and off to our potable water tanks. Okay. That's a submerged tube type. I'm going to be going on to a flash evap in a sec. Does anybody want to go over the submerged tube type multi-stage evaporator? Everyone feeling pretty good? Okay. Almost done, guys. All right. So again, multi-stage flash evaps. Same concept. We want to get as much heat out as possible. We don't have to follow it all the way through. All right. Still goes through a distillate cooler. Still goes through distillate condensers. We're still going through an air ejector. But the last thing, instead of having a tube's nest down here, we got a feed heater right here. All right. So we are entering in pretty much the same concepts. We are air dragging away any of the non-condensables. All right. Our second stage is sitting at a nice clean 1.7 PSIA. It's almost at a 30-inch vacuum. Remember, 30 is perfect. First stage is a little bit higher of a vacuum. It's at 23. All right. Our vapor is sitting at a nice 142. And the second stage, the vapor is at 119. We have no flash chamber here because everything is going to be a liquid as it comes through. And again, we have another salinity valve. Just because it's a flash evap doesn't mean that we shouldn't check and make sure that we keep ourselves accountable for what we're doing. We don't want to fill our potable water tanks with salt water. All right. But still the same concept is continued. We are entering this first stage above our boiling point. All right. Let me erase all the ink on the slides. All right. It's entering in at 172, but it turns to a vapor at 142. All right. The only way that it's not turning into a vapor right here is because it's under a pressure coming from that feed pump all the way back there. Okay. So we have multi-stage EVAPs on board the ship. We don't use them. All right. But you will see them on board. So we have 2 multi-stage flash EVAPs were once located on the TSES. One is now replaced with the aqua blue, and the other remains dismantled under a blue tarp. All right. But this is what they look like. All right. Nice big jumble of pipes. But from what we have here is from saltwater feed pump right here. We go to a distillate cooler right there. And then from there we go to our second stage condenser. From there to our first stage condenser. We come out, we go to an air ejector condenser. And now we're going into our feed heater. So this is where all that steaming takes place. And then to that, to the first stage flash chamber. And that's just the way the water travels before it even enters the flash evap. All right, and finally, let's talk about that salinity cell. So what we're doing is we have an AC source. We're turning that into a DC source using a transformer. We're basically using an amp meter. So we don't want current going in here. A higher current is going to go to a higher level. So if we have higher levels of salinity, it's going to make it have a higher current. All right. And that's not good. So that's what we're looking out for. And that's going to send a signal to the dump valve. So pure 0 ppm of dissolved solids. That means there is nothing in the water besides hydrogen and oxygen. There's literally just H2O floating around in there. All right. Distilled is a very poor conductor of electricity. It's the salts that conduct the electricity in the water. All right. As the salinity increases, the conductivity of the distillate increases. Seawater is a very good conductor. All right. A salinity meter measures current, although the meter scaled is in ppm. So as the current increases, we are going to have a more dense distillate, more salt water. So boiler water is very pure distillate. A 3-way dump valve is set to dump distillate to the bilge if the salinity cell detects impurities greater than 3 ppm. All right, and that's for boiler water. So as soon as it leaves the green, enters the red, the 3-way valve trips. And when it trips, that means it's going to open up and it's going to dump it into the bilge instead of sending it to our tanks. All right, and then the US maximum for drinking water are in excess of 500 ppm. Now, a salinity cell basically looks like this. On the TSES, it's just a nice little probe. It enters in. This is a very old-fashioned way of looking at of what these things look like. They are not that big anymore. I think the biggest one I've seen is about the entire thing sits inside of like this little like vitamin D bottle. It's really nothing too crazy. These things are quite large on these pieces on this ship. All right. So that is it. You guys have any questions on anything of that? All right. Other than that, guys, like I said, exam 1 is next Wednesday. So that's the 27th. There is no class tomorrow. There's no class Monday. That being said, we do have a quiz on Monday. Everything that we went over today. All right. You know, big awareness is that we are, even though it's day 4, we are in week 4 basically of how the normal semester feels. So keep that in mind as where you guys are at. Every day is a week. So already that deep into the semester, we only have 1, 2, 3, 4 weeks left. We only have a month left of class. All right. You guys are doing good on the quizzes. Today was a little 67 is not where I want it to be. So make sure you guys, if you're not getting stuff, ask questions. All right.
Quick question.
Yes.
For the quiz it's on Monday, even though we don't have class.
Sorry, Tuesday. Thank you.
Okay.
Yeah.
Just
So
check.
Tuesday is the quiz.
Okay.
Yeah. There's no class. Don't log into Zoom
All right. Cool. Thank you.
on Monday. All right. The 26th, I will see that I'll have a quiz. 4 will be on freshwater generation.
Okay.
Guys, ask questions, please. I'm sitting here just like you are, and I want to make it worth it for all of you. Okay.
What's the symbol? I saw it a couple times. That two like almost like backwards cell phones almost. I don't know how to like describe it. It's like use.
Oh, okay. That's an air ejector.
Oh, yeah.
Nope, that's not what I wanted to do.
Yeah, it said air ejector above it, but I don't know if that was like it just wasn't showing like a picture of an air ejector, if that was a symbol for it.
Yeah, that's the symbol for an air ejector. Let me just show it just in case. Come on. This symbol, right?
Yeah.
Yeah, that's an air ejector.
Okay.
All right. Okay. Any other questions? Again, guys, if I'm going too fast or if I'm going too slow, give me a heads up. All right. If you guys are starting to get a little nutty from sitting here for so long, give me a heads up so that way we can take a break. Like I said, it's 3 hours. We don't have to use all 3. 15-minute breaks aren't the worst thing in the world. Okay. Anybody have any questions before I say you're done? Okay. Just keep in mind there is a tutor for 540 as well. So don't feel that you guys have to do this alone. All right. Other than that, you guys are good. I will see you guys all on Tuesday. Come with questions for the review. Be prepared for the quiz on Tuesday. And we'll have the exam on Wednesday, all right?
Sounds good. Have a good day.
Have
Have a good one.
Have a good weekend. Good, guys, too. All right. I'm going to end it and then we'll jump into another call, right?
How should I get into the call?
I'll just email you the link.
Okay.
All right.
Yep.